In this video, we're going to look at differentiating the squared error. This is the function for the squared error here, and we've seen this in previous videos. When we talk about minimising e of w, we're treating e as a function of w alone. Now we've seen that whenever we looked at the graphical calculator. As we adjusted the values for our parameters w, the error value would go up and down. Now, the data points here, xn and tn, we can think about these as fixed, or if you like, we can think about them as constants. So within this function e of w, the values x of n and t of n are constants. So we know x of n is going to be the numbers, for example, 0, 0.1, 0.2, 0.3, and in the example we looked at, it went all the way up to 1. And the value for our tn was our original function plus the noise. So we can think about these as fixed terms or constants. So our goal is to differentiate this here with respect to these values EW. And then we're going to set the differentiated function equal to 0. And we're going to use this to find the weights that minimise the error. So we're going to form this partial e by partial wj is equal to 0. So let's go ahead on the next screen and we'll see how we're going to do this. So let's start the differentiation. We have our error function here, but we know within this function we have our approximating polynomial. So the approximating polynomial can be written in this form here and also in the summation form. So we can replace the y xn comma w with this summation here. So e of w then becomes this function here. And then what we want to do is differentiate this function with each of the values wj. So we're going to form the partial by partial wj of this function. Now mathematics can seem quite complicated and difficult, but if we break it down into little blocks and we know the rules, then it can become quite manageable. So the first thing that we're going to do here is we know that we can take the partial by partial wj inside the summation. So we can take it inside this first summation. Now we can't take it inside the second summation because we're going to have the squared term here. So we take it inside the summation and we get this line here. So we can bring the differentiation inside the summation term. So we can see that if, for example, we started off with looking at differentiating, for example, d by dx, the sum from 1 to 3 of ax to the power of 2. So what we could do is we could work out the 1 to 3 over ax to the power of 2. So a is going to be 1, so that would be equivalent to x squared plus 2x squared plus 3x squared. And then when we differentiated this here, we would get 2x plus 4x plus 6x, which would give us 12x. So that's differentiating outside the summation, but again we could then go ahead and differentiate inside the summation. So if we differentiated inside the summation, we would have the sum from 1 to 3 over d by dx of ax squared. So in this instance here, we can go through the differentiation first and then do the summation. So we would have 1, 3. Whenever it differentiated that, we would have 2ax. And then we put the values for a in, so that would give us 2x plus 4x plus 6x. Again, would give us 12x. So in this instance here, it doesn't matter whether the differentiation is outside the summation or inside it. So we want to differentiate this function here. Now with mathematics, it's best to try and simplify things as much as possible. So we can replace everything that's inside this set of brackets with a single term, and we'll call that term en. And then we can rewrite this line in a much simpler form, so that all of this has been replaced by en, and then it's been squared. So we've got en squared. Now we're going to start off by performing this partial differentiation here, partial by partial wj of en squared. Now we're going to have to use the chain rule in order to do this. And this is where people tend to get a little bit confused. We can think about this en squared as the axis up here would be our en squared, and it's going to be a function of en. Now it's quite a simple function of en. We simply square en to get en squared. But then we could write en itself is also a function of our values wj. So in effect, we've got a function of a function. So we're going to have to use the chain rule in order to do the differentiation. So we're going to have to differentiate our en squared with respect to en. And it's just a normal differentiation because we've only got one set of values here for en. And then we're going to have to multiply it by the differentiation of partial by partial omega j of our en. Now it's a partial differentiation here because the omega j has got lots of different values. So we can work through this differentiation. We'll end up with 2 en, and we're left with partial by partial wj of en. And that's what you see here. The final differentiation using the chain rule is going to be 2 en times partial en upon partial wj. Now we can take this here and we can substitute it back into our original equation up above. So that's going to give us the value of a half times the differentiated function, which is 2 en, partial en upon partial omega j. So the 2 and the half cancel out, and that was the reason for starting off with the value of a half in the first place, just so that this would balance out and we wouldn't get a constant term feeding in to all of the rest of our calculations. So what we have so far is partial e by partial wj is equal to the sum from n equals 1 to n of e of n partial en by partial wj. We want to now differentiate this here, partial en by partial wj. Now we know the value for our en is given by this here. We defined it earlier. So we're wanting to then differentiate this here. So all we've done is we've dropped this here into the equation above for en. And we know that the values here for our wk xn to the k can be written out in full form here, and this is our approximating polynomial. Now if we perform this differentiation, again we could take the partial by partial wj inside the summation and do the differentiation first and then do the summation. It doesn't matter which order we do it in. But the thing to notice here is that inside this sum, the only terms with the index k is equal to j will depend on wj. So all other terms are independent of wj. So it means that they're all going to contribute 0 whenever they're differentiated. So we can look at this in detail here. So if you did partial by partial wj of w0 xn0, we're going to get a value of 0. Because all of the other values j is going to be independent of the value omega unless the value j here is the value of 0. And the same here, unless the value for j is the value 1 in this equation here, then we'll get 0. So we're only going to get an output whenever the value of our partial by partial wj is the same value of the j here and the j here. If they aren't, then they're going to contribute 0 to this differentiation. So this is really a statement that the values w0, w1, w2 and so on and so forth are completely independent of one another. So when we perform this differentiation here, it turns out that the solution is quite simple. It's just going to be our xnj. So from the previous page, we have partial en by partial wj is equal to xn to the power of j. So we can substitute this here into this equation here, and it's going to give us this. Now finally we can replace the en with our yxn, w minus tn. So this is the final equation that we've been looking for over the whole of this video. So we're not quite finished yet. There's no point in generating a mathematical function unless we can get in and interpret it, and we can learn something from it, and we can get some intuition as to what it is trying to tell us. So let's imagine this problem. We have a point in three-dimensional space. So this could just be the room that you're in at the moment. Now we want to get to this point. So this point here, in effect, is our value Tn, where n is equal to 3. So we've got 1, 2, 3 axes for each of the values of our Tn. Now, we're not going to be able to get exactly to that point because we're going to use an approximating method. So we're going to try to approximate that point. And we're going to approximate that point by using a polynomial. So in our polynomial, we've only got access not to 3 dimensions, but let's say we've only got access to 2 dimensions. So that means that we can't get up here, but we can get close. We can come along this axis here, and then we can come down this axis here. And let's say we get to this point. But now there's a problem. We have this thing here, which in effect is going to be our y, xn, w. Now whenever we subtract one from the other, we're going to have this vector here. And there's a problem. We can't get from this point to that point because this is in a two-dimensional space and this is in a three-dimensional space. But what we can do is we can take this and we can map it back down into this lower dimensional space. And we can be sure that we can do this because we can always just come back up along here to get back to where it started. So now the problem is not getting from here to here. The problem is getting from this point here over to this point here. Now in order to get there, we can't go over this route. We can only go in rectangular. So we can go up this way and then we can come along this way here in order to get to this point. So this here is our error. It is the En in this equation. Now in order to minimise this error, what we're going to have to do is we're going to have to come along this distance here. Now this distance here is going to be given by our omega naught in this direction, and it's going to be given by our omega 1 in that direction. So whenever we go through this differentiation, it provides us with the omega naught and the omega 1, and it tells us how much of omega naught we need and how much of omega 1 we need in order to go from this point here to this point here. And that in effect is what our equation tells us. So forgetting about this one here, it's just the same as this equation up here. So in effect what we have up here is something called a dot product. So it says that if the dot product is equal to 0, then there is no component of the error in this direction, there's no component of the error in that direction. And in fact, if you're in any other higher dimensional space, there's no component of the error in any direction. In that case there, then, we're sitting at the correct spot. But if that isn't the case, as in this example here, there is a component in this direction and there is a component in that direction. So the dot product here determines the components of the error in each of the directions within our space. So if you have managed to get through this video, then well done. It's quite a difficult video, and we're not expected to know this as part of the book Pattern Recognition and Machine Learning. I'm not aware that it actually goes through this derivation, but it's a useful derivation to see at least once. Plus, in order to understand all of this stuff, it's really best been introduced in terms of n-dimensional vector spaces and subspaces. And it's actually quite easy and simple to understand it whenever you develop that mathematical maturity to see all of this in terms of vector spaces. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.